Hello folks, this is Pierre-André Mathieu, and today I'm going to go over an in-depth explanation as to how I set up a camera Devil May Cry 3 style, like the one you're seeing right now. Someone told me in the comment section and that he is confused as to how I set up a camera. I'm not gonna mention his name, but what he said here is he's confused as to how the camera is set up during sequence in the event tick variable. Did I drag out a function, a macro, or something? Well, the answer to that is I don't, and I'm gonna show you why. Okay, look closely within the character mesh. I don't have follow camera and camera boom because I already designed a camera system that enables me to do that, and that camera is called camera blueprint. I created this by going to blueprint class and select actor. You can rename it however you want, but I just name it camera blueprint for simplicity. Anyway, let's dive in there. I said within the first tutorial that I'm going to show you 3 different nodes in utilizing the camera. And what you're seeing here is what's called a collapse graph. Think of it as a folder of your code. It's a way of keeping your workspace tidy by grouping several different nodes into one single block. This dark gray box is labeled set location. It's a collapse version. Instead of seeing 10 plus messy nodes on your main screen, all you see is this very same one. This pop-up here on the right is a thumbnail showing you what's within this very node. It reveals a complex network of logic, meaning the background usually indicates it's inside a function or a specific organized graphic section. This little thing here, the execution pin, is the input trigger. When the game's logic reaches this point, it enters the collapse graph to run all hidden instructions inside. As to why I use this? Simple. Collapse grab prevents spaghetti code by hiding complex logic that I don't need to look at all the damn time. It allows me to label a big chunk of math or logic with a simple name like this, set location. Unlike a function or a macro, a collapse graph is usually unique to that specific blueprint and isn't necessarily meant to be reused elsewhere, just there to clean up the view. Now, I'm going to explain the difference between a collapse graph and a function so that way you won't be confused. Collapse graphs are best for local organization, a literal folder for nodes. It doesn't live in the My Blueprint sidebar. It only exists right where I made it. I can't reuse it in other parts of my blueprint or other actors. It's strictly for cleaning up the current view I have right now. It can have multiple execution pins, import or output, something in which functions cannot do. Functions are logics needed to use over and over and over again. There are specific mini-graphs that I can call from anywhere. If I change the code inside the function, every place I use that function updates instantly. There is a catch to it. If I can only have one what I meant to say here is functions can only have one execution output. Also, it can contain latent nodes like delay or timeline. It can be pure, which is green nodes with no execution pins, which is fitting for math calculations. Macros create custom logic gates or shortcuts. They are templates that the computer copy and paste into the graph at compile time. The catch here is that it's difficult to debug than a function because it doesn't have its own state in memory. Unlike functions, macros can use delays and can have as many input-output executions as I want, depending on what kind I'm making. Simply put, if I have a messy pile of nodes that I'll only use once in this specific spot, collapse graph is the way to go. If I'm calculating a value like health or performing an action I'll need frequently, all I have to do is make a function. If I need a custom if statement that includes a delay, for instance, all I have to do is make a macro. Okay, now that I explained the difference between collapse graph, function, and macro, I think it's high time I explain to you what each of these graphs can do, starting with set location. What you're seeing here is the logic inside the set location collapse graph. This specific setup is a classic way to create smooth movement for a camera or an object. But in this case, I'm using it for the character. Now let's break this down. This thing here, vector interp 2, is the star of the show here. Rather than snapping the object instantly to a new spot, this node calculates a smooth path between 2 points every single frame. Current takes the current location of the self. Target takes the location of another actor indicated by the blue line coming off from the screen. Interp speed controls how snappy the movement is. I multiplied a variable called log interp speed, which the value is 3, and multiply it by 1.5. Once the vector interp 2 calculates the next small step towards the target, the set actor location node actually moves from the object to that new coordinate. Because this is likely connected to an event tick, it creates the illusion of fluid motion. By the way, the target from the second get actor location is the character. Now this is where the potential gotcha comes into play. I have 2 get actor location nodes. This one here targets the self, which is the camera blueprint. This one here is targeting the player. And once I target that to the player, that's the destination I want to reach. If I accidentally plug the self in both, the object won't be able to move because it's already at its target. This variable here, delta seconds, is a stand-alone float variable plugged into vector interp 2, which is perfect because it ensures the movement speed is the same regardless of whether the player is getting 30 frames per second or 120 frames per second. Now, let's go over set rotation. This is similar to the logic set location graph, but with one critical addition: clamping. It's basically the standard for camera logic where I want to allow rotation, but prevent the camera from flipping upside down or rotating too far. Now let's break this down. First, the logic grabs the actor's current rotation and uses brake rotator. Rotations in 3D space consist of three axes. X, tilting side to side. Y, looking up and down. C, left and right. The clamp here is basically the safety guard. It's the most important part here, taking the Y pitch and ensure it stays between -60 and 60 degrees. Without this, the player might be able to rotate the camera 360 degrees vertically, which usually looks broken in game. By clamping it, I've essentially told the camera you can look up and down, but stop once you hit a 60-degree angle. This part is where I reassemble and smooth the camera. Make rotator puts the pieces back together. Now notice how X manually set to 0 here. This ensures the camera always stays perfectly level and never tilts sideways. Rotation interpolate is the most important part here. Just like vector interpolate, this makes the rotation smooth. It transitions from the current rotation to the target over time. Now, as for the interp speed, this is quite a high speed, meaning the camera will snap to its target rotation very quickly and feel very responsive. If you notice, my yaw is passing straight from brake rotator to make rotator without any changes. It means my camera can spin left and right infinitely. However, it's restricted only on up and down pitch axis. This is perfect for a standard third-person or first-person camera. I'm currently using get actor rotation for current and pin on the R interp 2 node. While this works, if the logic is running on every tick, it's often cleaner to store the desired rotation in a variable to avoid small calculation jitters. And finally, I can go over the camera zoom. This part is a very simple one. What this does, it handles the third component of my movement system, the camera zoom. Well, I've already said the name of the collapsed graph, but you get the point. Anyway, what it does, it specifically targets the spring arm component, often known as the camera boom, or called, however you want to put it, to pull the camera closer or push it further away. The breakdown in this is very simple. This blue node, the camera boom, on the left represents my spring arm. In Unreal Engine, the spring arm acts like a physical selfie stick attached to the character. The length of that stick is defined by the variable target arm length. This is where the calculation comes into play. F interp 2. Because the arm length is just a single number, I'm using F interp 2 This one here is the actual current length of the arm right now. This is the default arm length I want the camera to reach. By the way, the default arm length is 540 degree wise, but I'm not gonna get to that. What this does, it calculates a number where between the current length and the default length, creating a smooth zooming motion rather than a jarring jump. This last part comes into play. The set target arm length takes that new calculated number and applies it back to the camera boom. Like my other graphs, because this is likely running on every frame, the camera appears to glide smoothly to its default position. This setup is useful because this logic is essentially a return to center mechanic. Based on the variable it names, it looks like something in my game might change the camera distance. Maybe the player zooms in, out manually, or the camera hits a wall. Additionally, this graph constantly tries to ease the camera back to the default arm length at a speed defined by unlock interp speed. In my set location and set rotation graphs, I was interloping toward a dynamic target. Here, I'm interloping toward a default arm length. If I want the player to zoom in and out with the mouse wheel, I would usually change the default arm length variable with the mouse wheel and let this graph do the work of smoothly moving the camera to that new value. Simply put, this is what my tick variable system works. 3 graphs that work together make the camera feel high-end. Set location smoothly follows the player's position. Set rotation smoothly follows the player's gaze with safety clamps, and camera zoom smoothly maintains the ideal viewing distance. Now that I've cleared that up, let's put it to the test and see how it works. Yep. See? Just like the camera system you saw in Devil May Cry 3 and Devil May Cry 4. If you enjoyed this video, please like and subscribe to my channel for future tutorials regarding this, and keep in mind that what you take and learn from me is yours to do with as you see fit. Peace out, and I'll see you guys on the next video.